A hush falls over the crowd. The guy with the mic spots that immediately. Asleep. Oh, Mike's asleep. Thanks for coming. It's great to see 20 people in the classroom. That's just fantastic. Same as last week. We're pretty much on tap for the same result there. I'm going to welcome Dave back for a second thing after some announcements. I'm Gary Oberts, by the way, the developer of the class. Please quiet your phones if you would, so that we don't have you be the one that everybody looks at when it goes off and expresses their dissatisfaction. Restrooms, I'm sure most of you know where those are found up the hill in the first building there on the right. We have two dual approach to questions and answers because we have the Zoom audience and we have the classroom audience. So Dave said he'll take questions anytime from the audience, but just hold on until I get to you with a microphone, or if you spout it off too fast, then Dave's required to repeat the question by the flashing sign up here. At home, watching on Zoom, just put your questions in the chat box. I'll be monitoring those over at the computer, and I'll get those questions to Dave as soon as we can. Also, please fill out your class evaluations if you would for this class, Beach Science. And at home, just go to the chat box and you'll see a link that will give you to a feedback place that you can go to and fill out the form as well. We get those too. Also, we are videotaping, of course, all of these classes now. So you can go into the Remote Learning Center and go in there and see these presentations again if you would like to. If you have to miss something, or you want to go in there and check to see what's up with those. I've got to get this off. There. Speaking of presentations, Dave is done this week, but he's back next week on another class called Earth's Major Extinctions. And I think if you enjoyed this class, you really enjoy that class as well. And just to note, that's going to be next week, same time, same place. And then it's going to skip a week because of Thanksgiving, go to December 3rd. And it'll be 1:30, not 1 o'clock. We've had some early arrivals here, but it starts at 1:30, the same thing. Also this semester, we've got a class that may be of interest to you. It's new research from the UCI School of Physical Sciences. We've got 3 very outstanding young researchers that we're going to focus on for this class. And they very enthusiastically wanted to come and try out OWLI because they've heard so much about it, they said, which is nice to hear. So they're coming from UCI's Department of Earth System Science and Physics and Astronomy on topics that are going to include ecosystem disruption in the Amazon, climate dynamics and extremes, and way back in time to imaging planet formation. And all of those speakers, I've heard them all, they're all just fantastic speakers. So I think you would really enjoy those too. So with that, I'll just leave it to Dave and join me in welcoming Dave back.
Thank you. So is this too loud, Gary? Is it okay? Hey, so next week I'm going to talk about extinction things. And if you come, I promise you, you will learn 3 things that will just knock your shorts off. I'm serious. They are so shocking. And I won't tell you because then, that'd be a spoiler alert. But you'll go, wow, that's amazing. So 3 things. Okay. So that's next week. All right. So I'm going to start with review. The thing is about, I've done a lot of work on the geology of beaches, and everything's very natural to me over, the 40 years that I've been doing it. And obviously to you guys, a lot of it's new. So I like to review because, I'm not going to test you. If this was in, college, I'd make you memorize stuff. And since I'm not making you memorize, then reviewing stuff is probably in order. All right. Let's see if I can make this move. No. There we go. Okay, so we started off by defining what a beach was, and it's a pile of sediment that occurs on the seashore, lakes, or on rivers. And we said, well, not rivers. We were not going to talk about rivers very much, but we're really talking about the ocean beaches or on the seas. And, we could talk about lakes too, but they're pretty similar. I guess we talked about Lake Michigan, so that counts. Okay, and we talked about different types of beaches. We can have sandy beaches, muddy beaches, cobble beaches, or no beaches whatsoever. And we talked about a little bit and I'll review why you get a muddy beach sometimes and a sandy beach in other places. And we talked about two fundamental types of shorelines, the depositional shoreline where you see sandy beaches, and then erosional shorelines where you see wave-cut cliffs and offshore islands, little what are called stacks and arches and so forth. And that's Little Corona Beach, of course. And that's on the left is Huntington Beach. Keeping it local. And then for the depositional places where there are sands being deposited on the beach, we said the nature of the beach is very dependent on wave energy, or if the tides are really strong, or if there's a gigantic river nearby. So obviously, if Los Angeles had, the Mississippi River coming into it, the beaches would be very much different. It'd look more like, a delta than the beaches we're at. We reviewed what features of erosional shorelines are like at Corona del Mar, with the sea arches, little headlands sticking out, sea caves. I didn't show any examples. I even showed you a blowhole, an uplifted marine terrace, and we can see all of those things at Little Corona Beach. So the idea is that the area is being uplifted by tectonic forces, earthquakes and so forth, and the waves are cutting away at the cliff, hence the wave cut cliff. And they're also leaving behind some erosional chunks behind, which would be these stacks out here, and locally arches. And if you go around that little point there, the little headland, there's caves that you can actually see there. And there's a marine terrace is the previous shoreline that's been uplifted. So that was, we reviewed was a features of an erosional shoreline. We also talked about depositional shorelines, including these weird little isthmus of sand called tombolos, barrier islands, bay mouth bars, and sand spits. And we applied that to our local area. And this is Gough Island in South Laguna. And it's a tombolo. So there's a little island or a stack attached to the beach with a little isthmus of sand. And then we we also looked at the Balboa Peninsula. This is the Balboa Peninsula, which is a barrier island. And this is the Back Bay, or the Bay Area, the Newport Bay area. And we decided, is this thing here a spit or a baymouth bar? And we found out that it was actually a baymouth bar because this has all been dredged. So previous to this, this was actually a continuous across there. So the Balboa Peninsula is an example of a baymouth bar. Oh no. So Newport Beach has both depositional, which would be the beach areas here, and erosional shorelines. And this is all due to the tectonic structure or the nature of the earthquakes in the area that are uplifting and subsiding areas. Okay, our friend sand, we said that actually sand is, which we think of as just kind of that stuff on the beach. There's actually a classification system to separate the size of clays, silts, fine, medium, and coarse sand. And there's all this very exacting nature that tells us what type of sand we're dealing with. And we said that there's two types of sand in the world. There's the sand that's mostly quartz and different minerals. And then there's these carbonate sands, which are all fragmented living matter, dead living matter. So little sea urchin spines and clam shells and coral fragments, that's a foraminifera. Here's a pleissopod or a clamshell there, and so on and so forth. So carbonate sands are all from living materials, breaking down of living materials, whereas quartz sands is from the breakdown of rocks into the mineral components. Carbonate beaches are only found where it's nice to be an animal living in warm water. So they mostly around in the equatorial area, and they don't like river sediment coming in. So when you're near the Amazon, you wouldn't expect to see much carbonate debris, and near the major rivers of Africa and so forth. So you need to be away from big rivers and in warm water, and then you'll see a carbonate beach. So Hawaii is a perfect place. The Bahamas are a perfect place. You can see all around the Caribbean, Indonesian islands, there's lots of carbonate beaches. no. All right, so again, blow-ups of carbonate sand. Everything in here was once living. These are coral fragments, so plesiopods, that sort of thing. So carbonate sands come from the death of things that are living underwater. So here's some brain corals here, different types of corals here. And these things are broken apart by things like parrotfish that eat them and spit them out. And that's what all this sand here is debris from all these living animals and plants in this case. So this is a calcareous algae and has little plates in it, and those little plates make the sand. So the carbonate sands are essentially 100% living material that's, now dead. But now the quartz sands come from erosion from mountains. So here you can see we're up in the mountains and some granitic rocks are being weathered from natural weathering processes. All that debris during a rainstorm is going to run down into rivers and then get flushed down to the sea. So here we're up in the Yosemite area, and all this erosion of all this rock is being swept into the rivers here, and that material is being swept down to the sea. So when we get to this is the Santa Ana River that separates Newport Beach from Huntington Beach. During the winter storms, when we get those 5 inches of rain and so forth, this thing fills with debris, and that's how the sandy beaches of Huntington and Newport are fed, is through these rivers. And of course, the reason the rivers are so cloudy is it's because of all the suspended sediment and clays and silts that are being transported down, and then the sands are rolling along the bottom.
I think you said last time that you need to have strong flows for this to happen. But
so
everyday flows, but nothing's happening.
The question is, when do we get flows into the for example, the Santa Ana River? Yes, during the normal days like today, if you went down to the Santa Ana River, the water would be crystal blue clear. You'd be able to see the bottom. There's no sediment. And if you looked at little grains of sand on the bottom, maybe they'd be moving from the tides or little tiny waves. During a giant rainstorm, which we might hope we get some this winter, this would be flushing all this sediment down to the sea. And actually, I remember about 5 years ago, we had this tremendous winter where it was one of the greatest rainy winters we'd had in decades. And an actual island formed offshore of the Santa Ana River, this little sand island, which was all the material from these floods that had gone out the river. Here's the cliffs. Don't they make sand? No, they mostly make things like pebbles. They make a little bit of sand, but most of the sand comes in through river transport and stream transport. Okay, let's talk about different sands. These are 2 types of white sands. This is a white sand on Hawaii, and this is a carbonate sand. So that means that every single grain of sand there is some fragment of an originally living organism that's now been fragmented. This sand is from Florida, and every single grain of sand there is quartz. It doesn't have any other minerals in it, just quartz, which is a kind of an odd sand. But those are 2 examples of beautiful white sands that we talked about last week. We also talked about one famed pink sands of Bermuda and in the Bahamas. And they're pink because they have this weird little microscopic animal called a foraminifera, and this is called Homotrema. And that's what gives it its pink color, is the mixing of the reds and the whites to make the pink. We talked about black sand beaches. This is in Palos Verdes, near the Wayfarers Chapel, and in the Portuguese Bend landslide. This is the Portuguese Bend landslide up there. And this is a black sand beach. And the reason it's black is this cliff here is all basalt, which is a black volcanic rock. And as it weathers down here, it forms this beautiful black sand. You can get green sand beaches. This is in Hawaii. And the reason it's green is they have this weird mineral in it called, give me this, olivine. All right. This is the same mineral that you'd know as peridot. So gem quality olivine is peridot. And then other beach sands would be purple and red. All right, we had a lot of fun talking about pebbles. Remember pebbles last week? The exciting world of pebbles. And what we did is we concluded that pebbles on beaches tend to be either hot dog shaped, what we call prolate spheroids, or disc shapes, which we call oblate spheroids, or we call these hot dog shapes and pancake shapes. And the idea is that the beach pebbles are those shapes because they're basically, the sand on the beach is sort of like sandpaper, and the pebbles either roll on it like a rolling pin or slide on it and become disc shapes. This is opposed to in the river where they're bouncing along down a river and they tend to be more spherical and not so rounded, a little bit more angular edges to them. Then we had fun looking at these pebbles. Remember that? And we said, oh, those are, everybody in the room said, those are clearly river pebbles because they're not disc shaped, they're not hot dog shaped, they're not pancake shaped. They are more or less spherical, pretty well rounded. And then we are all shocked to find out that they were photographed on the planet of Mars. All right, and we'll talk more about Mars if you come to the next lecture. All right, then we started talking about, what was this last topic? The movement of sand. Why is beach sand mostly the same grain size? So look at this, you've got 100 yards of beach here, and it's all the same little sand grains, the same size. How does that occur in nature? When I was a kid, I remember people would say, yeah, they truck in sand, that's all that sand's fake, No, that's all deposited by the Santa Ana River during those floods. And so what we did was we started talking about how sediment is sorted. So if you started off with a big pile of dirt like this, and then a river came through and flooded this area and transported that big pile of dirt, we would recognize that some of the material in the dirt would be salts and it would just dissolve. Some of it would be in suspension, making the water brown and murky. The sand grains would be bouncing along in the flood. All right, because they're too heavy to be permanently suspended. And then the bigger boulders, pebbles, and cobbles would be kind of rolling and bumping along more slowly. So remember, we started with a big pile of dirt. This big pile of dirt is being moved by the flood, and the suspended sediments moving at the same rate as the water. The bouncing sand grains are moving a little bit slower, and the rolling and tumbling stuff is moving even slower. So this naturally separates the flow out into different grain sizes. And that's how this is the start of how we end up with beaches that are all the same grain sizes, because that current concentrates that grain size, and elsewhere you get concentrations of your pebbles, and the muds would get transported offshore because they're in suspension. All right. We also said that the flow of water over sand makes what are called bed forms, and you've all seen these. And I was a non-geologist once, and I'm sure I saw them, and I never appreciated, if you walk on a sandbar in a river on beaches, you walk on this little textured area, and those are ripples. And if they're bigger features, like here, these are larger features. These are called dunes, and they form in subaqueous as opposed to the wind dunes, the Arabian desert dunes. These are submarine dunes now exposed at low tide. So they're larger features. These ripples are in the order of, this high and spaced very closely. And here you can see bigger dune forms here and then smaller ripples forming at the same size. So we learn that sand, the flowage of water over sand can make all sorts of interesting features. Here's a larger dune form here as well. So there's all sorts of interesting things that can form when water and tides flow over loose sand. And they actually follow a certain pathway. So if you have sand here and the water's flowing too slowly, nothing happens because the water can't move the sand. And then at some critical velocity, you start forming the little ripples on the sand. If you increase the flow velocity greater, you get dune forms, which are the large scale ripples. And then finally, if you have even faster flowing waters, it'll just smear everything out and you'll get what's called a flat bed or a plain bed. So these are some of the features. So this would be ripples, slower flowing water. These are the dune forms, more rapid forming flowing water, and then the plain bed at the top. So this is all review again, hopefully. All right, sand on the beach or mud. We said that in a place where there's waves, there's lots of energy associated with breaking waves. So you tend to concentrate your coarsest grain size where the waves and the wave energy is the greatest. So that's why on a beach like Huntington Beach, you have those breaking waves. That's pushing all the sand up onto the beach. And that's why we have a sandy beach. But if we go to a tidal shoreline, that's not the case. In tidal shoreline, the way the tides move is they come up, and then they slow down, and they slow down. The tide's coming up, and the tide's slowing down. And by the time you get to the highest tide, there's hardly any current at all. And as a result, you tend to deposit muds up here, and most of the sands are down here where the low tide area is. So if you go into the Back Bay is a tidal estuary of Newport Bay. And everything's mud there because there's no energy there. All right. So, and then Balboa Island would be kind of like intermediate because you have some little waves breaking and you have the tides going in and out. So this would be sort of Balboa Island, and this would be like the Back Bay. Anyway, so you might expect in a high tide zone of a tidal area, some sort of muddy shoreline. And then in a river influenced shoreline, this would be in the Mississippi Delta, it's still a shoreline. All your sand is going to be concentrated in the channels where the river is flowing. And then after you go into the area outside of the active channels, this is all mud. All right. So the occurrence of sand in the shoreline environment is very much tied to the energy of the environment. You need flow energy to have the sand be deposited there. So if you wanted to find sand today, you'd want to go into that channel. You would never find sand here. Maybe in a storm, you might get a little bit of flowage from the, over the levees and stuff. But in general, this is going to be all mud. It's going to be sand here. In the tidal environment, you go to the lower tide areas to find the sand, and the higher tide, it would be more muddy and so on and so forth. So in summary, the shoreline is very different if you're considering wave, tidal, or river influenced examples. The beaches are different because the distribution of energy is different. Grain size in the shoreline environment is largely a function of the distribution of energy. And it's also dependent, of course, if there's sand around. If there's no sand around, then, that's going to affect things as well. But in general, it's very much a function of the distribution of energy. All right. And then we talked about waves on beaches. Is all this coming back to you guys? Yeah. And then we showed this beautiful diagram, right? And the idea is that we said that the wave size is a function of wind speed, wind duration, and something we called fetch. And fetch is the area over which the wind is operating. So if you're blowing across the entire Pacific Ocean, that's a thousands of mile fetch. Whereas if you're just blowing across a small pond, that's a very short fetch. And as a result, you can't get big waves in a pond, whereas you can in an ocean. So they plotted it here, the fetch length here. So if you had a small lake that's 2 miles across and you had wind speeds of 20 miles, in that little 2 mile across lake, you might expect to see waves maybe a foot tall. All right. Now, now you're talking about a lake that's 100 miles wide, and you're talking about a 20-mile-an-hour wind, here you might see 6-foot waves. All right. And then if you're up to, 1,000, a small ocean or a small sea that's 1,000 miles across, a 20-mile-an-hour wind might get you 10-foot waves. Does that make sense? Yep.
Is it reasonable to expect that the wind will blow over
Absolutely not. So for example, the big storms that we have, that when we get 20-foot waves in this neighborhood.
Dave, can you remember to repeat?
Oh,
your
sorry.
question?
Excellent. What's your name again?
Frank.
Frank. Frank asked, is the entire Fetch area always involved in wave generation? So the idea is the Pacific Ocean. Oh, you're going to get a microphone and you'll say it better than I.
Might as well just sit right here, Frank.
There you go.
Will wind blow over the entire area of the entire length of the fetch?
No. For example, when we get 20-foot waves at Huntington Beach or 15-foot waves, typically that's from a storm in the North North Pacific that might be 500 miles wide or 300 miles wide. So it is, you know, you've seen those big storm gyres. That's about the size, the maximum size. It's not going to be over the whole Pacific Ocean. And the same thing goes for those tropical in the south, in the summer swells we get. You know, you'll see those tropical gyres down in the southern hemisphere that cause us to get waves. Those will be like, you know, 100, 200 miles across.
Then how do you forecast what the size of the waves are going to be? How do you know how far that wind is going to blow?
Now, there's a service called surfline.com, and they actually predict wave height. But the way they do it, now there's first of all, you can do it this way. So if you know that your wind speed, you know what the wind speed is. Okay, so actually we could do it from this diagram. So there's a gyre near the equator, and it is 100 miles across. And we know the wind speeds are going to be, say 50 miles an hour. So you'd say, oh, you're going to have waves of 20 feet. So you could actually use this diagram to do that. And it's very ballparky because, you know, what's actually the fetch and all that sort of stuff. But you could do it. But what surfline.com does, they actually do it to predict surfing contests. So they want to know how big are the waves going to be? When is the swell going to hit? They want to know all the real facts. And you know how they do it? They don't use this. You know how they do it? No, they don't guess. That was how we did back in the 60s. We used to guess. No, what they do is use buoys. So they'll actually have, there's buoys all across the ocean for shipping and other issues. So they can actually see the waves coming and they say, oh, the waves are now off of Seattle and they're moving at X number of miles per hour. So that means they should hit LA by, you know, Thursday or something like that. So it's become a true science. I think it's pretty much an empirical science, meaning that it's all based on observations, not based on like math. But yeah, it's very much evolved. Great questions though, Frank. Thank you. And then, so this is in Nazaré, and there's a guy in Portugal, and there's a little tiny guy about this. This is something like 100-foot wave. And this was from some giant storm in the North Atlantic, and it's hitting down now in Portugal. There's a wonderful HBO series on this. Have you seen it? Called The 100-Foot Wave. It's about 8 episodes, and it's all about the idiots that try to surf this. I mean, this is terrifying stuff. What's that? Question? Okay. All right, and now here's the example we used for fetch length and wave height. We said that in Lake Michigan, you have fetch length across the lake in that direction. So when the winds blow towards the east in Holland, Michigan, versus from the northeast during the winter, you have difference in wave height as predicted from that previous diagram. And these are the waves in Holland, Michigan, when the wind's blowing across the fetch that way. Whereas if you do the entire length of Lake Michigan, you can get 25-foot waves. All right. Okay, then we talked about currents on beaches. We talked about rip currents. The idea behind rip currents is the waves are pushing water up on the beach. And the beach, and what happens is the water, some of the water goes in, it percolates into the sand, but a lot of the water comes back and it naturally self-organizes. So the water has to flow back because there's water moving in and water moving back. So what it does is it it forms these what are called circulation cells, where the waves break, push water up, and then they move longitudinally along the beach, and then they move out, and where they move out, they're called rip currents. And the water, it tends to dig a hole there. The water gets deeper here because of the flow out like that. The waves seem smaller here, and everybody wants to swim here, but they don't realize that the current's going to drag them out to sea. So here's an example of spaced rip currents. So these are the rip currents, there, and so forth. And the idea is the waves are pushing water up here, the water's flowing along the beach, and then it flows out. So up like that, and then out in that direction. And that's the concept of a rip current. And of course, the lesson that you all know is you never, if you're out here, you don't try to swim in this way, you try to swim here, and then the waves will actually push you in. We also talked about wave refraction, or the bending of waves around headlands or on submarine topography. So here's waves bending around this headland there. And so here you can see the waves. If you look at any one of these wave crests, they bend here. The reason they bend is waves, when they're in shallow water, they're dragging on the bottom and it slows them down, whereas a wave in deep water isn't dragging on the bottom. So the waves in deep water move faster than the shallow water waves, and you get this bending of the waves that you can see here. The interesting phenomena that occurs as a result of this wave refraction or bending is you can form these longshore currents. So what this does is it pushes water and you get these strong currents. When we get big waves at Huntington Beach, both in the winter and the summer, you can get flows as strong as a river. So you can, and people don't realize this, you know, if they're not from around here, they'll swim out and they'll be down the beach 100 yards within 5-10 minutes. And then they'll and then they'll swim back in and they go, where's my car? You know, because not realizing the longshore current. Word. How did I get word? That was an interesting one. All right. Okay. When waves go up on a beach, they can also reflect. So we're talking about wave refraction. We talked about wave diffraction last week. We can also talk about wave reflection when a wave bounces off a wall. So when I yell, the sound waves bounce off the wall. Well, a water wave moving in that direction also would bounce off the wall, and it can form a lot of dramatic spray as a result. And it forms all sorts of beauteous images as one wave smacks into the other one, shooting them both up in the air. So that's wave reflection. We talked about beach changes over time. During the summer, when the wave energy is less, you tend to deposit sand on the beach. But then in the winter, when the wave energy is greater, the energy profile extends much into deeper water, so it changes the slope of the beach. So if you have little waves, you'll have a little shaped sloping beach, but with big waves, you have a large sloping beach. And what happens is you tend to erode the beach face to spread out that sand into deeper water because the waves are bigger. And that's why when you go to the beach now, you might see little cliffs that are 3 or 4 feet high. That's because the wave energy has changed and the beach is no longer in equilibrium. And what you're doing is this sand is being spread out into deeper water. Okay, examples of waves. We talked about big waves. In the summer, about 5 times a year, you can get enormous waves. This is the mouth of the Newport Bay. And you can see these are 10 or 15 foot waves. There's a guy standing there. So if he's 5 foot, that's, you know, more than 10 feet tall. But this only happens a few days a year. Right over here is this famous surf spot called the Wedge, where the waves bounce up against the jetty and then double in height, as we'll see in a minute. So this is Big Corona. So this is the Newport Wedge, where the first wave bounces off the jetty and reflects and hits the second wave behind it. So you get constructive interference And you end up seeing things like that. So that's our own little Newport Beach, you know, in the summer. And this happens every single summer, and they get waves that big every single summer, just enormous waves. The other interesting thing about it is the waves break in about 5 feet of water. So that's like a 20-foot wave, and it breaks in 5 feet of water. So the amount of energy, you know, normally you'd want to have some space between you and 20 feet of water, but this breaks right on the sand and causes all sorts of challenges for people trying to ride the waves and so forth. All right, so that was our review that I spent 35 minutes on. All right. Tides and beaches. Okay, now we're going to talk about, so we talked a lot about waves. Tides also dramatically influence beaches as well, even at Huntington Beach, Newport Beach, and so forth. So what's it with tides? Tides are formed as a result of gravitational attraction of the sun, mostly because of the sun and the moon. So the idea is both the moon, you know, so you have, here's the earth, here's the moon, the gravitational attraction is pulling on each other, right? All right, so when the sun and the moon are aligned, the gravitational attraction is really strong. If they're not aligned, then you have weaker tides, right? So here's the case. This is called, okay, anyway, this is called what's called a neap tide, which is a more gentle tide. And then this is a spring tide when they're aligned. And we'll take a look at them in a minute. Okay, so here's spring and neap tide. So a spring tide occurs typically during a full moon when the moon's pulling the water mass of the earth, actually bowing it. So this is the water mass. All the seas on the planet are being pulled by the moon in one direction and pulled by the sun in the other direction. And this is when we have our greatest tides. If they're opposite, and the moon's pulling on the tide this way and the sun's pulling in the tide this way, the tides are damped out. And that's what we call a neap tide, N-E-A-P. And these are the times, full moon versus new moon and so on and so forth. To me, it's most dramatic when you see, you know how you can see the sun going down, and you can also see the moon rising and the moon going down. Well, if you see the sun going down and the moon going down at the same time, that means you're going to have giant tides. So because if the sun and the moon are in the same position, that means that's the maximum pull on the tides. All right. Otherwise, if you see the sun going down and you see the moon directly overhead, that means that you're in neap tides. The tides aren't going to be that strong. So what is that? Yep.
That doesn't seem to be the case in these two exhibits.
Yes, it does. So this is spring tide. They're pulling. This one's pulling this way, this one's pulling this way, so you have the maximum amount of. No, either same side or opposite sides. Yeah, because remember, gravity doesn't know whether you're on both sides or on the opposite side. Gravity's just saying, I'm pulling you on you, and here they're both on the same side pulling. Here they're pulling on different sides, but the same deformation of the tides is going to occur between this example and that example. And in this case, you have a tug of war going on where the moon's pulling here and the sun's pulling there. You can see this, it's much more circular in terms of the tides because the tides aren't as strong. Does that make sense?
No.
All right. Give it to me. Give it to me.
Well, if they're both on the same side, you have two masses pulling the same side.
Yeah,
okay?
yeah.
And here, the moon would tend to negate what the sun is doing.
No.
Because water flows all over the earth.
Okay, if there was no moon at all, no moon at all, this water would still be expanded like that.
The same way?
Yeah.
Now that's really hard to believe. I mean, how could it be pulled out on that side when there's nothing pulling it out in that direction?
Huh, that's an interesting point. I don't know. This is too, we're getting to physics now.
Okay, all right, let's go on.
Oop. All right, so this is actually a tidal record for Newport Beach. And this is the number of feet here. A 6 foot high tide is pretty high. Just the other day, about a week or two ago, we had a 6.8 high tide, which is, pushing as high as I don't know if it's ever gotten to 7, maybe it gets to 7 feet, but it's a 6.8 is a really high tide. All right. So, but you can see this week here you have, and by the way, notice that every day, each one of these is a day, you have 2 high tides and 2 low tides. See that? So 1, 2. Now this is a really high tide, really high tide. So if you're over 6 foot, those are really high tides. Notice, so these would be your spring tides here. And then notice here, your tide's only getting up to about 4.5 feet, maybe 5 feet. So these are the neap tides here. And you can see here's where the moon and the sun are interfering with each other. Here where you've got negative tides here associated with the super high tides. So whenever you see a super high tide, you will see an associated super low tide. All right. And you can see when you're in these flatter periods, you don't ever get negative tides and you don't ever get super high tides. But here you have a whole week of these extreme tides, and that would be your spring tides. And of course, when you're having these maximum tides, that's the maximum amount of, it's not just like water going up and down. That means that the water's flowing in and flowing out because you're moving the water up 6 feet. But in, for example, the Newport Bay, that means you're going to flood into the back bay, miles, because you're lifting the whole sea level up. So let's take some examples. Here's a little Corona at high tide. So at high tide, most of these rocks here are covered up. And then at low tide, those are those same rocks. You can see they're all exposed. So high tide, low tide. And oh, this is a famous up in Sunset Beach. Do y'all know where Sunset Beach is? That's the northern part of Huntington Beach. There's subsidence going on, and they've had a lot of massive flooding events associated with king tides. Now, I wanted to check this out before this lecture. One theory is that this is, normal sea level, global rising sea level that's affecting this. But the other story I heard was that there's an oil field there named the Seal Beach oil field, and they were sucking out the oil, causing the land to subside. And I've heard recently they're now injecting water into the subsurface to try to expand and lift up the area. So I'm wondering now if these massive flooding events that occur at Sunset Beach have been rectified a little bit or mitigated. But anyway, this is a flooding at king tides in Sunset Beach. This is, more Sunset Beach area. This is Balboa Island during a really high tide. So that's the seawall here. It's much higher than the street level there. What they, I always walk around Balboa Island. What they've done there is they've raised the sea levels about 6 or 8 inches because they're concerned about land subsidence and global sea level rise. And that's probably given them another 30 years of fewer problems. Here's another picture of the king tides. Oops, goodness gracious. Wow. All right. There. Why is this happening?
Just click on it, Dave.
I can't. I don't have control of the mouse. Can you tell the lady, is she doing something? Somebody's pulling
Lucy?
on it.
Yeah, she's monitoring. Lucy,
Hello, yeah.
there. Question over here, Dave.
All right,
I was wondering.
Susan,
Yes.
thank you.
In places like Mont Saint Michel in France, and I know there's a place somewhere in Maine, I don't recall the name, the water is goes down really fast and then it rushes right back. Bay of Fundy, thank you.
Ah,
Is that the same? Is the same?
we're getting to that.
Oh, you are? Okay.
All right. One of the things about king tides is when you have big waves and king tides, that's disaster. And I'll give you an example. Do you remember July 4th, not last summer, but the summer before? Big waves actually broke over the Balboa Peninsula. So what happened is we had a king tide and we had 20-foot waves or 10-foot waves coming in. Remember a boat washed ashore by the Newport Pier broke apart? Remember that? You guys watch the news, right? All right. And anyway, what happened is they have a big pile of sand there up at the Balboa Pier, and that thing got eroded down by the big waves and the high tide, and the waves were actually breaking over the Balboa Peninsula, flowing in about 3 feet of water into the back bay. So there was actually waves breaking over the Balboa Peninsula by pavilions. Fascinating. So anyway, that's an example of what happens when you have big waves and king tides. They work together and they can really make things nasty. Here we go. And of course, we've all heard about Venice, Italy. Venice, Italy is affected by global rising sea level, but also by the fact that the land is subsiding there. So they get a sort of a double bogey where the land is subsiding, sea level is rising, and they're having more and greater problems with sea level. So wave character changes from high tide to low tide. This is the same day. This is at San Onofre Beach, trestles, lowers. And this is at high tide. You can see the waves are having problems breaking. And the reason is the water is so deep that they can hardly break. And then at low tide, they don't have that problem. So adding all that water actually changes the way the waves break because the water is deeper all of a sudden. This is at Old Man's in San Onofre as well. At high tide, the waves aren't even breaking because the water's too deep and they just kind of crumble onto shore. Whereas at low tide, they break much further out. Again, both are on the same day. All right, back to Susan's question. Weird waves, tidal bores. So the problem with tidal bores is as follows. Say, here's your beach here, and the tide's going to go up, say, 10 feet and down 10 feet. So you got 10 feet of vertical motion every day, has to happen twice a day. But you have some sort of estuary that's 10 miles long. So that means that you have to go up 10 feet and down 10 feet twice in a day over 10 miles of distance. So what happens is here the tides can rise up, you know, and there's no issue. But here you got all that 10 feet of water has to flow down the tidal bore or down the tidal channel here. So you have to do that really quickly. And what happens is you get waves. So these are called tidal bores. And what's happening is this is basically high tide here, and this is lower tide here. And this is the high tide coming in as a wave. And the reason is it has to cover this whole area relatively rapidly because you have to do the 2 tidal cycles in a day. But of course, there's a good side to this. This is a tidal bore in China. And this is an advertisement. All right, all in one meal. All right, skip ads. Not now. I'm going to make you guys buy this. Okay. So this is in China. This is 3 minutes long. And this is a tidal bore in China. So this is Chinese decorations. And this is the tidal bore. So that's the tidal bore. They're just writing that that's the wave associated with the tide. That's not an ocean wave. That's not a breaker. That's the tide coming in. That's the tide coming into a river channel. So some of these places, these tidal bores can get 10, 15 feet tall. So of course, this makes for interesting viewing. And all these people are along the cliffs watching the tide come in. And you can, rent jet skis and you can go in front of it. And of course, we have our surfers riding the tidal bore. And you can see what tide, about 8 foot, something like that. This might be on my bucket list for something to do. Again, this is not a wave like Huntington Beach. This is the tide. What's that? Oh, she kicked out. And then here's the boat trying to get through the tidal bore. Look at the size of that wave. And again, that's not a wave, that's the tide coming in. Well, you can imagine this is every American's dream, right? Every surfing American. And of course, you'd have to worry about the pollution in the water and everything else, but what a fascinating concept. All right, how's that on tidal board, Susan? Well, that's coming at probably 20 miles an hour, right? Yep. Oh, it's going to be a hard question, I can tell.
Not really a question, it's a comment. If anybody ever has a chance to get to France, at the border between Brittany and Normandy, there is an old abbey called Mont Saint-Michel. At certain time, every day it happens, but at certain times of the year, it's even more pronounced. We were there when the tide was about 20 feet.
Wow.
And it's Mont Saint-Michel is normally on solid land, but after the tide comes in, it's an island. And you can, if you're there when the tide is coming in, you can look out, you're looking across the English Channel, and it's just solid land, and you see this wall of water rushing toward you, and eventually it takes about a half hour from when you can first see it, and it gets to you, and it's under 20 feet of water at that point. Just an amazing sight.
Thank you. All right, enough of this. Escape. All right, beach cusps. So if you walk on a beach, and these occur on the Newport beach as well, these things are called beach cusps, and they're little piles of, they look like teeth sticking out from the beach into the water. And they're very curious things. This is at Crystal Cove. And you can see the beach cusps, 1, 2, 3, 4. They're very equal. They're beautifully spaced. They're very rhythmic, and they're very common. Isn't that amazing? They can be made out of, this is sand and gravel. These are pebbles, and these are cobble cusps. So they can be all sand, or they can be mixtures of sand and cobbles, or they can be all cobbles. So our beaches. Okay, now I'm going to take you on some walks I've taken on Newport Beach. So this is our field trip part of the class. So this is a beach, and this is the breaking waves, and the layers of sand under the beach are basically parallel to that black line. As a beach grows, beaches can grow very similar to tree rings. So you can get layers of sand like that as the beach grows into the body of water. All right. So very similar to tree rings, beach laminations can move towards the breaker zone. But what can happen is, and here's examples of, if you dig a trench in a beach, you'll see that there's layers of sand, and these layers of the sand are the ones that I just showed you in the previous picture, right? But what happens if the wave energy changes and you start to erode those layers, you cut those layers off. And then if you walk on them, what do you think you'll see? So you're going to walk, it's low tide now, you're walking right here, and the layers of sand have been cut by this erosional surface. What do you see in your feet below you? What's that? You could. You see stripes. So this is on Balboa Island, and these layers are those layers that we saw here that have been truncated. And now we're walking along the beach and we're going to see those layers forming stripes on the sand. So these are the stripes. So the water is down here. This is low tide, high, the up beach is that way, down beach is that way. And these are layers of sand that have been cut by an erosional surface. These things are called swash marks. So when the waves move up, they push sand and they push bubbles up and they form these little lines. See the swash marks? So these are called swash marks. See them all sorts of them. We're going to see all sorts of stuff you've walked over a million times and never saw. Okay, here's some better swash marks. Now this black stuff here, I had a friend who went to the beach recently and she said, there's oil everywhere. And I said, no, that's not oil. Those are heavy minerals. So one of the features of waves coming up and stopping and then withdrawing in the swash zone is they push up these heavier minerals. A lot of times they're magnetite. You can pick them up with a magnet and so forth. But anyway, it's really, so this isn't oil at all. This is all natural material, but these are the swash marks that are formed. You can also see there's a lineation. See the lineation? And that's telling you the flow direction of the swash coming in. So swash marks and lineation. Here we are walking down by the Newport Pier. This is low tide. This is a sandbar. And remember we talked about barred beaches the other time? This is an actual sandbar at low tide. Here's the longshore trough. The longshore trough is where the rip currents are fed. So here's where the longshore current would come, and here'd be where the rip current channel would go out. All right. Another picture of it. Some ripples. See that sand ripples? Clam carpet. Here's for you. So this is an example of a whole bunch of little tiny clams forming a carpet. They're all alive and they're burrowing into the sand, and then they stick their little feet out and they feed during higher tide.
Now, what are the little dots? Are they?
These dots?
Yeah.
I don't know what those are. These are the clams.
Yeah, right.
I don't know what those are, but we'll see similar things in a minute. But I do know what they are. Okay, here's again heavy minerals. All that black stuff on the beach are heavy minerals that are pushed up by the swash. Some of the heavy minerals are so concentrated in Alaska, they actually mine them because they have valuable ore in them. Now this thing is really cool. You see this thing? This is called an air dome. We're going to study that here. Okay, so the wave came up. Here's the swash line right there. See that? Here's a footprint. Here's some more swash lines, right? Now what happened was the sand was dry. The water came up and it percolated down and there's air trapped. So the air tried to escape and it makes these little domes all along here. All right, so this is what happens is the water rushes over dry sand. The air gets trapped and it tries to move upward because it's more buoyant than air. And it actually deforms the surface of the sand and you get these little air domes. Yep. No, I think those are all down footprints. I think it's just a weird camera angle. Actually, if you take your finger and you push them, they go. It's really fun if you've never done it before. Then it gets boring after a while. But anyway, all of these little air domes, if you push them, they deflate. And here you can see some of them have little holes where they've naturally deflated, so they've leaked air. These were described in a paper by a guy named a famous professor at USC back in the 1960s. You want to take a break? So I taught this class previously at the Oasis in Newport Beach, and everybody went running down to the beach hoping to find these air domes. And the key thing you have to understand is you only see these air domes when the tide's rising onto dry sand. So if you go down there and the tide's falling or something, you may not see them. It has to be the swash is coming up onto the dry sand to get the little deformation. They form all sorts of odd patterns. So here's the swash here, and here's a whole, a whole little cluster of these little tiny air domes. It's almost art.
Well, how come it's in that one area? I always thought those are animals underneath.
Everybody does. Everybody says, oh, those are, what are the sand crabs? Sand crabs. Yeah, no, those aren't sand crabs at all. Those are little air domes. And if you go up and you push them, they go like that.
But they're just there. They're not there.
Yeah, well, now you're starting to talk the physics of the problem. Why is it in one place and not? So now if you wanted to investigate this, it becomes a scientific problem. What's the distribution? What's the spacing of the air domes? There's all sorts of things you could do. But the problem is, the sad thing is why? If there's not like a reason people yell at you. I mean, there's a lot of interesting science you can do, but unless you can justify it's going to change the world somehow, they yell at you. Here's another one. So here's swash. Now we've got seaweed getting pushed up in the swash zone. Here's that little swash here. Here's a whole bunch of air domes here. Notice all the seaweed is in two orientations, as we talked about previously. The rolling orientation where it's parallel to the shoreline, and then the flow direction orientation where it's parallel to how the current was actually moving. Okay, so air domes, swash marks, seaweed oriented. There's more. You're going to see more. Yeah, seaweed orientation. So this is parallel to the flow. This would be perpendicular to the flow. And that's the swash line there. A couple of air domes there. Splash marks. So this is from, see the little splash mark here in the sand? So what happened is a wave in the last throws, it kind of threw up a little bit of water and it formed this interesting pattern with the little bubble marks. See the little bubble marks on it? And I did not do that. That was natural. You're going to accuse me of faking things. And then of course we see some lineations in the sand down here. That's from the flow. I don't know what caused these patterns, but they're gorgeous. I really don't know. If they were flow, you'd expect them to be all very parallel. And these are, it almost looks like a fracture pattern, or I don't know what it is. These things are interesting. You're up in the swash zone here in Newport Beach. These are called anti-dunes. Remember we talked about dunes that form, you have the ripples that form and then the larger scale dunes. Well, these dunes are called anti-dunes and they form at high velocity flows in very shallow water. And that's what's happening in the swash zone here. So these are called anti-dunes. They actually move in the opposite direction as other dunes. Yeah, but that's another problem. Anyway, those are anti-dunes. More anti-dunes. Now, these things are interesting. These are called rill marks. So these things are like little tiny valleys. Okay, this is, inches something. This is maybe an inch across. This is like a little tiny valley. All right. And here's the up end of the valley. See that? So this is uphill in this direction. And you can see that the valleys get deeper in this direction. Why is there a valley there? So this is low tide, and you've got valleys, little tiny valleys forming in the sand. Little valleys this big. See them all? Look at that. They go for feet down. Okay, so you guys are confused, right? Okay, Why is there a valley? Something caused the erosion to form the valley. And clearly the culprit would be either air, wind, or water. So it doesn't look like it's windy today. So it's water. Where's the water coming from? Where's the ocean? How can it be forming valleys if the water has to be coming? See the problem? You know what, in a river valley, the river's flowing down the valley. Where's the ocean flowing down these rivers? So you're all puzzled, right? Okay, here's what's happened. At high tide, all the water seeped into the sand, right? So at high tide, all this sand becomes enormously wet. Tide drops, the water's up high now, and it's saying, wait, what am I doing up here? I'm water, I flow. So the water leaks out of the sand and it flows out, and as it goes down further and further, this flow gets greater and greater. So the water actually comes out of the sand from high tide and then flows down and forms these little valleys. Isn't that amazing? So the idea is the water was trapped at high tide in the pore spaces between the sand grains. Then the tide drops, all that water is gravitationally unstable and wants to flow out. So it flows out and it actually forms this little erosional pattern. Kind of cool. Again, nothing that's going to change the world, but if you walk along the beach and you see these rill marks, you say, oh, water leaking out of the sand. So here's a close-up of some of these little tiny valleys. And it's all from water leaking out of the sand, high tide going to low tide. I promised you more obscure things. Here's some swash marks. See these little patterns here? That's from foam popping. So, the white water that comes up, as those little bubbles burst, they make little foam marks in the sand. Again, an interesting curiosity and something you can look at. I mean, there's so much to see on you think of sand, a sandy beach, what's there to see? There's all sorts of stuff to see if you look. So these are all from bursting bubbles in the foam. Foam marks, here's some really nice ones. So these are the foam marks here. And swash marks, beautiful swash marks here. And some sand lineations, and my shoe. And both shoes, yes, a special deal, you get both shoes. Yeah, those are beautiful foam marks. And Terry, Sue, you can see we have the famous inverse footprint there again. Terry Sue was saying that these things look like they're bulled up footprints, but they're actually subsidence. Again, more foam marks and swash marks. Lineations. So a lot of times in the sand, we see lineations. There's a very complex origin about turbulent flow on a barrier. And actually, they can observe that in shearing flows of water, they form little lineations, and these sand grains are apparently aligned in the flowing water along the boundary of the lineation that forms the lineation. So there's actually one of my professors when I was in grad school wrote a paper on the origin of those lineations. Again, we're in the heavy mineral zone, up in the shore zone, in the swash zone. More lineations. Wait, there's more. All right, orientation of shells and sticks. So you can see the shells are oriented like that. The sticks are oriented like this, and some of the shells are oriented parallel to flow like that. So following our previous discussion of pebbles, more lineations. These are an interesting feature. Again, there's so many weird things that occur. These are called rhomboid structures, these little V's. And they're another feature of the flow. I've never understood what causes them, but you see them quite often on the beach. So those are called rhomboid marks. Here's some pretty good ones. The little V shapes. Air holes. Sometimes you get the little air, the domes forming up. Sometimes you just get the little air holes where the air leaked out. These things everybody thinks are the sand crabs, and they aren't. That's the air coming out. And you could, when you see them forming, you'll see little bubbles of air coming out of them. More air holes. And we're on Newport Beach, and here we see a pretty good size erosion, little feature of the beach from changes in wave conditions. And here you can see lots of footprints, but here's the beach cusps as we go along that way at low tide. All right, so that's the end of the feature on quartz beaches. And for the rest of the presentation, we'll talk about carbonate beaches. Now, say what? Okay, carbonate beaches, these are what you visit on your vacations, right? So we'll talk about reefs. There's basically three major types of reefs. Reefs are areas of dense growth of different plants and animals along shorelines. And we can talk about fringing reefs, which are reefs that occur right along the shoreline. We can talk about barrier reefs, which occur kind of like barrier islands in the quartz sand area, which are further offshore. We can talk about atolls, where the whole island is subsided and all you have is the reef left behind. So it looks like they're big like donuts because there's no central island anymore. There's just the reef around it. And what's happened is the island has sunk by subsidence, but the reef has kept growing upward because, you know, it's a life form. So it's going to grow upward. And that's how you get an atoll. So here's some examples of different carbonate beaches. So these would be fringing reefs here. This would be a barrier reef here. This is basically an atoll here. So fringing, well, that's really a barrier reef more, I'd say. Volcanic Island Lagoon, here's your barrier reef that's offshore, and your back reef area, which is behind that. And here's your examples of patch reefs. Patch reefs occur between the barrier reef and the fringing reefs. They're just any reef that occurs in between, and they're called patch reefs in that case. All right, so more examples. This is the same picture. I was like, gosh, I recognize that picture. All right, fringing reef. So these are reefs that are attached to the shoreline. So here's your fringing reef here. And, you know, if you were vacationing here, you'd walk off here, put your snorkel on, and you'd start swimming and seeing the fish and the different corals there. And again, a barrier reef would be similar to a barrier island, where you have a shoreline where you build your houses. Here would be your lagoonal areas. Here would be your barrier reef, and these would be patch reefs inside of the lagoon. So different parts of the reef that we can just ignore, I think. Beautiful view of patch reefs. I think this is in the Great Barrier Reef area. And again, these are all individual patch reefs on the order of 100 yards across, a couple hundred yards across. There's a lot of geologic studies that are associated with studying reefs, and partly because a lot of oil fields occur in fossilized reefs. And they need to know about the distribution of, you know, where the best place to drill wells are and so forth. But the interesting thing is they've sent geologists, like I've had colleagues, and I've been on a bunch of field trips myself. They send these guys out, and these guys hang out on coral reefs for like, you know, months, a year, trying to understand the geology and the biology of the reefs. And what they've noticed is there's if you have a barrier reef like this, here's the lagoon, and then the shoreline would be here. There's all sorts of changes in the geology of the corals and the life forms that occur as you go from the fore reef to the reef front to the reef crest. Now, when we talked about quartz sand about the nature of beaches associated with quartz sand, we said it was the wave energy that really dominated, whether you got coarse sand or mud or pebbles and things like that. It's the same thing in a carbonate environment. The nature of the corals that are growing and the life forms that are growing are very much a function of the energy distribution. So you can imagine that at the reef crest, that's going to be where you're getting the strongest wave energy. Offshore, you'd have less wave energy, but still significant wave energy. In the fore reef, you're in deeper water where there's less light and less wave energy as well. In the back reef area, you probably have different nutrients that are occurring in the waters and in the lagoon and everything. So it's a very diverse area, even though it's relatively not a very large distributional area. So here's some examples of the different types of corals that occur in a barrier reef. So up in the reef crest area, we see things like encrusting corals. The idea is that the wave energy is so strong that any fragile type of coral will just break off. So you'd find the more fragile corals like the branching corals in deeper water where the wave energy is not so great. In deeper water still, you might see plate-like corals because the amount of light getting down in deeper water isn't as much. So they form plate-like structures so they can absorb the maximum amount of light to help them grow. And then at the base of the reef, you might see a bunch of debris getting shut down by breaking waves, breaking up the chunks, animals and plants chewing up the dead coral and then spitting out sand, which would occur down here. And we have massive corals here, bindstone encrusting glued together in the high wave energies. And then in the back areas, we have some geologic terms we don't have to worry about. So this would be an example of platy corals at the top, and these would be ones you'd find in the deeper water setting like that. Again, another geological description on the left, showing very similar types of descriptions. Here's an example of a brain coral, which would be a massive coral, which might be found in the upper part of the reef. And then these branching corals, that's a thing called Acroporus cervicornis or staghorn coral, might be found in slightly deeper water where they have some wave energy, but not enough that'll break the coral. Those individual horns there are, they're made out of rock, the calcium carbonate rock. So you might, I don't know, I've never tried to break one, which wouldn't be ecologically the correct thing to do, but they're pretty hard things. These things are just, massive. You could smack it with a hammer and nothing would happen. I'm confused. Those were examples of corals and other living organisms on a reef. Where's the sand? Right? We're talking about sand here, right? Well, this is a parrotfish, and there's all these videos because people are amazed that parrotfish come to these nasty looking corals and they have very strong teeth and jaws, and they bite off chunks of the living coral and then they poop out sand. So, from a geologic thing, it's like a wonder, how do you form sand? Ooh, it's parrotfish poop. And to me, as a geologist, I don't find it that curious, but we all appreciate the parrotfish for doing the work of making the sand for us. So apparently a ton of sand on coral reefs is made through parrotfish poop. They poop sand. And again, as I mentioned previously, there's types of calcareous algae that once the algae dies, it leaves sand behind. So this is Halimeda, and every one of these little green things has, if you remove the organic coating on it, has a little plate of calcium carbonate, which will become the sand. And basically, if you pick up this handful of sand, it's all plates from this Halimeda or this calcareous green algae. And this is another, here's a close-up. And again, every one of these sand grains here is a plate made up of one of those guys. So this is another way of forming sand in the carbonate environment, is through the decay of these calcareous algae. Again, showing what a Halimeda looks like. This is pulling one up and examining it. And then the idea is that they break apart, and these are the sand grain sizes. So two ways of forming sand now are parrotfish poop and calcareous algae. Yeah, this is an important point. Quartz sand grain size is a function of first of availability of the sand grains, and also where the currents are strongest. So when we see a coarse sand versus a fine sand, we say, oh, a coarse quartz sand is where the currents are stronger. Any geologist will tell you that in general. In a carbonate beach, the grain size of the sand is really a function of what died. So if Halimeda died, it forms big plates. Halimeda is the green algae, whereas the parrotfish poop might be a different grain size. So the quartz sands are a function of the energy of the currents. The carbonate grains of sand, the size of them is really a function of what died. It's kind of an interesting difference. Okay, some other life forms on or near the carbonate reefs. This is the staghorn coral, Acropora cervicornis, and occur usually around 30 feet of water. Other examples, beautiful stuff. And these would be your brain corals here. Oops. Elkhorn corals are kind of like staghorn, only they have these broader branches. This is Acropora palmata, and they form these larger branching features. You can see the water depth there is maybe just a few meters or a few feet. And there's some fish, Acropora palmata. Here's a whole field of Acropora palmata, or the Elkhorn coral. And here's the famed brain corals. Looking like a brain, hence the name. Other features, this is called a finger coral, which they look like they're about the size of fingers. Different examples. Sponges. Sponges also occur on carbonate reefs. And you might say to yourself, sponges, who cares? I mean, you know, they're actually, they feel like sponges. And you look at them and they go, oh, they're kind of odd and they're soft. And you don't think much more about them, but they're very important. Here's why they're important. There's this one sponge called Cleona that eats old shells. So this is a clam shell, and all those holes reflect the fact that Cleona, the boring sponge, was making its life from eating the decaying pleissopod shell, the decaying clam shell. What happens is that weakens the clamshell, so you could pick that clamshell up now and just crush it with your fingers, and that would form another way of forming sand. So there's things like these boring sponges that actually take dead things, eat from them, and result in destroying their structure and their strength, such that they can become sands as well. So we're finding out how to form sand in a carbonate environment is from the parrotfish poop, from the calcareous green algae, and also things like Cleona, the boring sponge, can break things apart, weakening them so much that they are easily comminuted into sand.
The holes are not the sponge.
No, those are basically feeding, basically,
Result.
exactly
Sponge
right.
is left.
Yeah, basically they're tooth marks or something equivalent. Again, oh, here's an interesting one. So here's our Halimeda, which is forming these larger grains of sand down here that you can see. one of the questions they had was, okay, you make sand by parrotfish poop and Halimeda and Cleona and stuff like that. How do you make carbonate mud? How do you make, so you can make sand grain size stuff, but how do you make stuff that's finer than sand? So there's these great arguments that came up, and they said, the way you form carbonate mud is the actual calcium carbonate comes out of solution, like a salt. It rains out of solution. No, that was a wrong theory, but that was one of the theories that was proposed. The latest theory, the last 50 years ago, is there's another thing. This is called a penicillus, and it's another type of green algae. When it dies, it forms mud. It has these little tiny needles in it, and as it dies, it forms mud. So as an interesting question is, people are saying, how do you form carbonate sand? Well, how do you form carbonate mud, which is, really fine sand? Because once you make sand, it's really hard to break it up into mud-sized particles. Remember, mud is just really, really, really fine sand. Plesiopods, all right, on the reef. Sea urchins. This is a sea urchin called Diadema. It's poisonous. It's a nasty looking sea urchin. And I've surfed a lot. I used to live in Puerto Rico, and there's Diadema everywhere. And I've never got one in my foot. So even though they're nasty looking and they're poisonous, in that if they got in your foot, you'd probably get infected. I've never interfered with one. On the other hand, in California, I've probably stepped on 10 and got 10 in my foot. So those are sea urchins in tropical waters. So again, carbonate sand is a result of all these life forms on the beach created by the parrotfish, boring sponges, and the calcareous algae. And again, all of these are different life forms. Conclusion. My conclusion. So next time you go to the beach, we hope you can appreciate a little bit more of the geology and the physics behind the beach. I mean, each one of you could have gone to one of these places, and now I'm hoping you'll start to ask questions about the geology associated with each one. I think that's the last slide.